Okay, I kind of failed to motivate why we are studying relativity to start with in electromagnetism. So let me just mention why we are interested in, why we are repeating these things. Now, the question that we would like to answer is, let's just take an example, point charge. Let's say, imagine there is a point charge at rest over there in this reference frame. It creates an electric field, it won't create a magnetic field. Right? So it's not moving, it's at rest, so there's no magnetic field, there's an electric field, it's an electrostatic problem. And then let's go to our reference frame in which we are moving relative to our initial reference frame. But in this reference frame, the electric charge is the charge is not at rest, it is moving with a constant velocity. So it will be creating an electric field plus a magnetic field. So in one reference frame, we have only electric field. In the other reference frame, we have only magnetic field, not only electric and magnetic field. So now the question is, well, this kind of shows that if we are trusting Maxwell's equations, and we believe in relativity that all the laws of nature should be the same in every reference frame. So this tells me that the concept of the electric field and magnetic field is a frame-dependent quantity. Electric and magnetic fields, they change from frame to frame, just like simultaneity and length, they change from frame to frame. Electric field and magnetic field, they also change from frame to frame. Now the question is how? How do they change from one frame to the other frame? So that is what we would like to study. Now, of course, to address this question, we will be looking at, let's say, the Maxwell's equations. So first of all, the first postulate of Einstein tells me that the Maxwell's equations should be the same equations in every reference frame. And what we are eventually trying to find will be the electric field in this new reference frame should be a function of the electric field and magnetic field in the old reference frame. Similarly, for the magnetic field in the new reference frame should be a function of the electric and magnetic fields in the old reference frame. This is the kind of relation we are looking for. Now, E prime and B prime, they satisfy the Maxwell's equations in the new reference frame with the new coordinates x prime, y prime, and z prime, and t prime. And special theory of relativity tells me that x prime, y prime, and z prime, and t prime, they are different than x, y, and z. So if you want to relate these two equations in the hope of obtaining some possible solution for E prime and B prime, we need to find some way to relate the coordinates and their derivatives. So at least that will be one way of approaching the problem. Now, another problem that we need to address is, for example, charge density and the current density. They will be frame-dependent quantities. Now, just to say the least, well, the velocity is a frame-dependent quantity, and current density is velocity times the charge density. Well, velocity changes from frame to frame, so the current density should be frame-dependent, just by looking at the frame dependence of velocity. Now, the other problem is the charge density is also frame-dependent quantity. You see, let's just imagine some charge density in this volume at rest in this reference frame. Well, if you go to another reference frame in which this charge density is moving in this direction, well, you see, initially it had this length in the direction of its velocity in its rest frame. In this new reference frame, it will be length contracted. So the volume that the same charge occupies is now smaller. Well, that means that the charge density should increase. So charge density itself is also a frame-dependent quantity. Now, of course, to be able to precisely specify how they depend on the frame, we have to specify how the length change. So that's kind of the first idea. That's why we are studying how length and how time will be changing from frame to frame. Of course, we can just jump these discussions if they're all already familiar, you are all clear about all these Lorentz transformations, length contractions, etc. But I would rather repeat them. So that if you have any questions, you can just ask them. Now, probably we will just finish today anyway. So the Lorentz contraction, the time dilation, the simultaneity we had already covered. Now let's start with time. Time dilation. Now you see, another thing about this relativity, the concept of relativity is that it basically states that, let's say there is one reference frame which is inertial, and if you are moving at constant velocity relative to that inertial reference frame, and let's suppose that you are in a closed room, you don't have any way of looking at outside and your velocity is constant. So if you just take this train analogy, the railroads are very smooth, there are no curves, no bends, no nothing. So it's just smooth at constant velocity. So, and if you cannot look outside, there is no way that you can tell, no experiment that you do can tell whether you are moving or not relative to the first reference frame. That is basically the idea of relativity. So for example, when we are studying the time dilation, we will be looking at this example. We will build a simple clock which uses light. So the light, let's say it starts from here, reaches the bottom mirror and reflects back. Yeah, it just reaches the bottom. Let's ignore the reflection. And the time it takes, let's say in this reference frame that is inside the train, will be, let's say this distance is d, it is d over c. Now we will see that for an observer at rest in the station, this clock runs slow. But that is not due to this clock model we are studying. It's anything that you can use to measure will run slow. For example, you can use a pendulum to measure time. That will also run slow, just like this clock. Or you can use your heart rate. That will also go slow. Or you can use your aging. That will also go slow. Or whatever you call living. That will also go slow. For example, we had this example of the twin. It goes to some star, comes back. For example, the twin on Earth will live 40 years, let's say. The other twin will age just 1 year, but the other twin only lived 1 year. It's not that he had lived 40 years, but aged only 1 year. He just only lived 1 year, whereas the twin on Earth lived for 40 years. Because if these different clocks would differ, then the observer inside the train would just look at this difference between these two various clocks to tell that he's moving relative to the observer on the station. But this concept of relativity says that there's no way he can tell the difference. So that's why all the clocks are slower. Even your brain functions are slower. Your aging is slower. The pendulum is slower. The electronic clocks are slower. The mechanical clocks are slower. Everything slows. And for that reason, it's enough to consider a simple timing system. You don't need to consider anything else, because if any other timing system would give a different result than this one, that would be a means of telling whether you are moving or not. But the principle of relativity tells us that there's no way of telling that. Now, this is inside the train. What the observer sees inside the train, the time between two events. That the light is emitted and it is absorbed over here. They differ by this much in time. Now, for the observer on the station, this is what he will see. You see, these are both moving with a velocity v. the light is emitted from here. This is at t is equal to 0. Let's say this is at t is equal to delta t, and the light will reach this point. Now this distance is again d. Are we sure that that is d? Maybe length has contracted. How do you know that in the perpendicular direction to the velocity, length is not contracted? How do you know? Well, that is what you had learned in 202, but how do you know? Okay, that is what you learned in 202, in modern physics course, but how do you know? How did Einstein know? Einstein didn't take the modern physics course. Okay, Lorentz proved it. Lorentz proved it using Maxwell's equation, but there's an easier proof. Okay, nobody is reading the book, I can tell. There is a nice example in the book, nice thought experiment. It says that, let's imagine this one. There is a wall on the station, and there is some, let's say, red straight line, horizontal line on it. You are in the train, you have your brush, you put the brush out of the window, and the brush will hit the wall. So you have the paint you have is, well, the wall has this red line, you have blue color on your brush. So let's consider two observers. Let's assume that in the perpendicular direction, length also contracts. So you are on the train, you put your brush out of the window, so the length is contracted, so blue color goes above the red color, according to you. Okay? For an observer on the train, on the station, you are moving, so your length has contracted, blue color goes below the red color. This is the observer on the station. Then you take your train, go to some city, and come back to the same station to compare your results with the observer on the station. Well, you will say that blue is above the red, and he or she will say that blue is below the red. If length contracted in the perpendicular direction. In this case, in this thought experiment, there is no problem with simultaneity, etc. You don't assume anything is simultaneous, but then there is a contradiction. So blue color is either above or below the red color. It cannot be both true at the same time. And then you say that to avoid the contraction, there cannot be any contraction perpendicular. To avoid the contradiction, there cannot be any contraction perpendicular to the direction of velocity. So because of that, I know that this separation for the observer on the station is d. It is also d for the observer on the train. So they are not different lengths. There is no length contraction in the perpendicular direction. Now let's look at this case. This is d. The distance it covers is v times delta t. So this length that light covers is d squared plus v times delta t squared under the square root. So the time it takes, the time between these two events. You see, we are comparing the time between events. An event is something that happens at a position at a given time. For the events are that the light ray is emitted in one of these places and it's absorbed on the other plate. And the time between these two events for an observer in the train is just d over c. And the time between exactly the same events for an observer on the station would be, let's just call it delta t, would be square root of d squared plus v delta t squared over c. Now let's solve for delta t squared c squared, or delta t squared is equal to delta t bar squared, this is d squared over c squared, plus v squared over c squared delta t squared. So delta t squared is just gamma times delta t bar squared, where gamma is 1 over 1 minus v squared over c squared under the square, gamma squared. Well, that's what I have over here. But you see here I have the squares. That's why I have gamma squares under the square root 1 minus v squared over c squared. Yes. This is 1 over gamma squared. Questions?
Şimdi buna göre hocam dışarıdaki observer için içerideki zaman yavaşlıyor.
So what does this tell me? Let's just imagine that we have this, the mirrors or the emitters and the absorbers, their separation is so huge that from the time that light is emitted until the time that it is absorbed, your watch just makes one tick, 1 second. Okay? So you watch the train move. Your watch makes 1 tick. The light has been emitted, but it didn't yet reach the other end. So his watch in the train didn't yet make that tick. So his clock is running slower than my clock when I look at his clock. Okay, when I am looking at his clock, keep in mind that if you take a telescope and look at his clock, the light emitted by his clock will take a finite amount of time to reach me. I make corrections because to that delay, and still his clock will be running slower. If he is moving away from me, for example, he will look redder because of the Doppler effect. He will shift red, etc. It will take some time for the signal to reach me. I make all those corrections, and then I conclude that his clock is running slower.
O zaman hocam buna göre hani correction'lar falan yapıyoruz ya, o zaman bir galaksinin de şu anki pozisyonunu ölçemez miyiz?
Of course, you can correct it. You see, you can look at the nearest star is 4 light years away. When you look at it, you see its position 4 years ago. Now, what is its velocity in the subsequent 4 years? Do you know? I don't know. Maybe some alien civilization just destroyed the star. We don't know. So that's why we cannot extrapolate it. Here in this problem, we are saying that the train moves at constant velocity. So we know its velocity as a function of time. Now and also in the future. Yes. You see. Yes. Now that's how we learn about nature. We make experiments. Now, people didn't like the idea. They wanted to get rid of it. But as it turns out, it works. I mean, you see, these observations are verified. For example, we have these particles that we call muons. They are unstable particles. And even if they move at the speed of light, if you ignore this time dilation, I mean, they can only travel a few meters before they decay. They become electrons and neutrinos, etc. Now, these muons, many of them are created at the top of the atmosphere. When we have all these cosmic rays hitting the top of the atmosphere, they create muons. And, well, the atmosphere has a thickness, at least. Because you can, by experiment, at least you have probably also made that experiment. If you fly, if you took a plane, the planes usually fly at 10 kilometers, so the atmosphere should be thicker than 10 kilometers, to say the least. The muons created at the top of the atmosphere, they reach the surface of the Earth, traveling tens of kilometers. So the only way to explain this is this time dilation. Since they are moving close to the speed of light, their internal clock has also slowed in our reference frame. So they don't decay so fast, so they don't decay after such a short time. They live long enough, in our reference frame, they live long enough to reach the surface of the Earth. Now let's look at length contraction. How do you measure length? Okay, the problem is the meter stick. I mean, you see, what we want to do is compare the length of this object in one reference frame with the length of the object in the other reference frame. With a meter stick, the only thing that you can say is that the you just take some segment of the meter stick, and you can only say that, okay, so there are these two things. Let's say this is the object that you want to measure. Okay. So in one, you take the meter stick, you bring it, attach it to the meter stick, and measure the length. But that is in the rest frame. Now, how do you measure it when it's moving? Do you take the meter stick with the object? Well, in that case, the meter stick will also get shorter. So how will we measure still? So let's see. You are sticking with the idea of the meter stick. Okay. So this is the meter stick. And we have this object that has, let's say, the length L. And let's say it is moving with speed v. This is length L when v is equal to 0 in its own rest frame. And then you are saying that, okay, it will, when it reaches over here, I look at this point. How do you look at it? Okay, so you are observing from here. How do you know that it's at the other end? You see, basically the idea, the problem here is you have to make sure that two events, in this case we have the two events that the back end is aligned with the beginning of the meter stick, and the front end is aligned with some other point. So these are the two events. So we should make sure that those two events happen at the same time. That's kind of one question we have. But let's just try to do it a different way. Okay, so let's just, here we will have some problems. Let's use light. It will be easier to measure. So this is what we will do. This is our object. We send some light. There's a mirror at the other end. It will go to the other end and bounce back, and it will reach this point, at the same point again. It will take a time, delta t bar. Let's say the length is L, and it will take a time 2L over C. So this is the time it will take for the light ray to start from one end, go to the other one, and come back. Do you agree? Now let's go to the other reference frame. So we have my object. We have our object, length L. So at this point, the light rate starts. At this instant, let's say this is t equal to 0. This is t is equal to t1. It reaches the mirror. But the object had already moved a distance vt1. And this is the time at t is equal to t2. And at this instant, the light rate is back at the initial point. So this is at T2. So this distance is V of T2. Now delta T, which is equal to T2 by the way, is the time that the light rate takes to start from one end, go to the other one, and come back. In this new reference frame, let's say my object has a length L prime. I don't know whether it is equal to L or not. We will see. So this is equal to T1 plus T2 minus T1. Now the reason why I separate it into two parts is T1 is the time it spends moving in this way. T2 minus T1 is the time it spends going the other way around. So this is equal to, well, T1 is L prime plus VT1. Well, let me just solve those first. L prime T1 is equal to L plus VT1 over C. L prime plus VT1 over C. This is what T1 is. Because you see, L prime is the total length the light ray has traveled L prime, and also it traveled this time VT1. This is the total distance that the light ray travels until it reaches the other end. So divide by C, it is the time it takes T1. Well, this tells me that T1 times 1 minus V over C is equal to L prime, or T1 is equal to L prime over 1 minus V over C. So we know what T1 is. Now let's look at T2 minus T1. Well, basically, T2 minus T1 is the time that the light ray took to reach the beginning after being reflected. So T2 minus T1, the light ray in total has traveled the distance L prime minus V times T2 minus T1. This is the total distance that the light ray has traveled, because my stick is moving in one direction, the light ray is moving in the other direction, so it traveled a distance less than L prime divided by C. So this tells me that T2 minus T1 is equal to L prime over 1 plus V over C. Now delta T is equal to T2 is equal to T1 plus T2 minus T1, which is T1 is L prime over 1 minus V over C. T2 minus T1 is L prime over 1 plus V over C. So delta T is equal to L prime over 1 minus V squared over C squared, which is gamma squared L prime.
And the unit of delta T is time, but the unit of L prime is meter.
Oh, okay, sorry. Here I have a C. This is my delta T. Delta T bar was twice L over C, but I know how delta T bar and delta T are related. Delta T bar now let me just make some corrections over here. So what is wrong? Well, we had before said that delta T bar is gamma delta T. So here we have delta T bar is equal to 2L over C, which should be gamma times delta T, which is twice gamma cubed over C times L prime. So apparently there's something wrong. What is wrong in our derivation?
Hocam delta T dediğimiz T2 diye anlaşılan aldım. T2 eksi T1 diye almamız gerekmiyor.
You see, what do I call delta T? The time it took to start from the light, from the source, went to the mirror and bounced back, the total time. Now, that is how I define delta T. Now, how I define T1 and T2? It starts at T is equal to 0. At the time T1, it reaches the mirror. At the time T2, it is back on the source. So the definition of my delta T is T2. What is my mistake? Now, let's see. We already know the result, right? So does this result make sense? Now, if the object is moving, the speed is, v is non-zero, so gamma is larger than 1, delta t bar is larger than delta t. So this result seems to be correct, right? Now let's look at this result. Now, delta t bar should be larger than delta t, right? Well, that doesn't really tell us much. Well, the result should be 2L over C should be equal to 1 over gamma. 2 gamma squared L prime over C. But if you take delta t bar is equal to gamma delta t, you don't get this one. Let's see what T2 minus T1 is. Well, T2 minus T1 is our time. So it doesn't travel L prime, but during that time, the rod had moved by V T2 minus T1, so the light ray traveled this much. This is the distance that the light ray travels, so we divide it by C to obtain the time it took. So T2 minus T1 should be equal to this one. Well, if I just move it to this side, I get T2 minus T1 times 1 plus V over C is equal to L prime over C. Okay, I forgot this C. So T2 minus T1 is also correct. So delta T is equal to that sum. If you just sum them up, well, 1 minus V over C, 1 plus V over C, they cancel. You end up having this 2. In the denominator, you have the product of these two, which is 1 minus V squared over C squared. But that factor is nothing but what we called gamma squared. You see, gamma is 1 over square root of 1 minus V squared over C squared. So without the square root, it's just gamma squared.
Hocam bir şekilde çıksan mı? Şurada mesela...
This one.
Evet. Işık değdi ya aynaya. Bu aynadan inip kaç bir şey değişiyor.
Well, you see, this distance is what I call V T2 minus T1. Now, L prime is the length of this rod in this reference frame in which the rod is moving. L is its length in its rest frame. L prime is its length in the moving frame. So this distance over here is L prime minus V T2 minus T1. And this distance is L prime minus V T1. This distance is L prime plus VT1. So in a time t1, the light travels the distance L prime plus VT1. In a time t2 minus t1, the light travels the distance L prime minus V times t2 minus t1.
Zaten onu veriyor.
Hı. Then what are we doing wrong? Well, what did I do? Delta T bar is the time measured in the train. In the train, the rod is at rest. So the light starts here, goes to the other end, and comes back. So it covers a distance L and another distance L. So it covers a distance 2L with the speed c. No, the L is the length at the rest frame. L is its rest length. So that is why I have 2L over c. L prime is its length in the reference frame in which it is moving.
Ama delta bar yani o hareket eden refleks frame göre değil mi?
Yes? No, you see, let's go back to our definitions. Now, delta T bar, the quantities with a bar on top, is the measurements inside the train. I go inside the train, I look at the light rate, it starts from the top, goes to the bottom, and goes up. Or it starts from the top, goes to the bottom. I measure the time inside the train, I'm moving with the train, so our delta T bar is d over c. In this example, I'm in the train, moving with the train. This is my length L, so delta T bar is the time it takes for the light ray to go and come back. So it covers the distance 2L with a speed c, so delta T bar is 2L over c. Then I go to the station. In the station, I measure the time. So that time is what I call delta T in the station. And for the times, for the first clock, we find that delta T is equal to delta T bar over gamma. So gamma is larger than 1. Oh, hold on. Yeah, gamma is larger than 1. No, hold on, there's a mistake over here. Delta T bar over gamma is shorter. So there's a mistake that I made over here, somewhere over here. Delta T squared 1 minus V squared over you see delta T squared is equal to 1 over 1 minus V squared over C squared times delta T bar squared. If I make this definition, gamma is this one. Here I have a gamma over here. So here is 1 over gamma. So delta T bar is 1 over gamma. So delta t bar is 1 over gamma delta t, or 2L over C is equal to 1 over gamma L prime over, no, times twice gamma squared L prime over C. C's cancel, 2's cancel, gamma's cancel, so L is equal to gamma L prime, or L prime is equal to 1 over gamma times L. So L prime is smaller than L. So that's what we mean by length contraction. Now, basically, now we have everything we need to write down the Lorentz transformations. Now, let me leave it for Friday. Now, any questions? Who will show up on Wednesday if we have a recitation? Okay. Last week there were only two people. So see you on Wednesday.
Burada ben hala şey anlamadım. Şimdi hareketli şeyin ölçtüğü uzunluğa göre kendi zamanını